Hi everyone. Um, so today I thought I'm going to go over the first midterm. I heard a lot of students struggled um, with the exam, and if you can't make it to my sessions, I felt like it might be good to just make a video on the midterm. And yeah, so you can use this to review for the final exam whenever that happens, and this video might be kind of long because there's a decent number of problems, and I think I'm gonna go over them with like lots of detail. But if I do miss something, you can ask me in person or you can message me, and I'll be glad to help. So so let's go over the first one. So let f of x equals root x. Okay, and then a, find the average rate of change of f of x with respect to x over this interval from 4 to 9. So let's just look at this problem, piece by piece. So the first thing that I'm looking at is, let's see, what is average rate of change? Um, so average rate of change has a formula. So average rate of change. And so the formula is y2 minus y1 over x2 minus x1. Subscripts don't matter. As long as you're consistent in like what you define to be the second point and the first point, then you're good to go. Okay, so this is what average rate of change is. It's this thing. And then it says, with respect to x over this interval from 4 to 9. All right. I think a lot of people got confused with this notation. 4, 9. Right? And I think lots of people thought this was a point. Unfortunately, it is not a point. It says right here, interval. But I guess I can like lead into the question, what is an interval? The way I like to think about an interval is like this. Let's say you have a number line and you have numbers on it. 0, 1, 2, 3, 4, blah blah blah, 9. So this is a number line, right? And and if you think about like, well, what's a graph? I'm probably gonna have to draw into here. So if you think about what a graph is, well, it's kind of like two number lines, like one number line going left and right, and one number line going up and down. And what a function is that if you take an input from one number line, it gives you a certain height on the other number line. So for example, our function turns out to be root x, and these are our x's. Well, if you plug in 4, you should get a height of 2 on this line. Anyway, so an interval will specifically be the x number line, the x-axis. And the interval from 4 to 9, well, it's specifically talking about this section right here. Right here. So we don't care what's going on over here. It doesn't matter. And we also don't care what's going on over here. Specifically for this problem, because it wants the interval from 4 to 9. So let me erase some of this stuff. I'm getting in my own way. Okay. I think it would be useful to know, what does the graph of root x look like? By the way, if you don't use the graphing calculator, like you don't even need one of these fancy ones, these like $100 ones. Your phone does it for you. You can just Google graphing calculator. You can pull up GeoGebra. Okay, so let's look at the graph of root x, and that's what it looks like. One way I like to remember what root x looks like is, we all know what at least hopefully we all know what x squared looks like, right? It's a parabola. And what root x is basically I take this parabola and I topple it over onto its side. And like, well, since it has to be a function, I can only choose one of those. And by convention, we choose the top part. Anyway, so we just take this and then we we rotate it 90 degrees over, and that will give you root x. So you start with x squared, you rotate it 90 degrees, and it'll give you root x. Okay, so going back to the question, from this interval from 4 to 9, I'm going to type in x equals 4 and x equals 9. And so, like, what is an average rate of change? The average rate of change, if I could draw, let's see, how do I draw? Sorry. Okay, there we go. Average rate of change is, well, I choose 2 points on the x-axis from 4 to 9, and I put a point at those two like x values, and I draw a straight line between those 2 points where it hits the graph, and that's my average rate of change. So that's like geometrically what's going on. But the question is, like, sure, that's what's going on geometrically, but how do I find it, like, using algebra and like pen and paper and stuff? So that's where this formula comes in. It's y2 minus y1 over x2 minus x1. And like it's not too bad to calculate this. So y2. Oh, before we go on to the y's, a really easy one to find is right here, x2 minus x1. So these are our x values. So let's say this one is x1, and let's say this one is x2. It doesn't really matter which one you label, as long as you keep like which x value corresponds to which y value. That's the only thing that's really matter. It doesn't really matter which one you set first, as long as you keep them consistent. That's what I'm saying. So if x2 is 9 and x1 is 4, so then y2 should be the square root of x2. Well, because of function of x is equal to the square root of x. So that's the square root of, well, x2 is 9. So that's equal to square root of 9, which is 3. And then y1 is equal to the square root of x1, which is equal to the square root of 4, which is equal to 2. Okay. So if we go back to our graph, well, what is this point? If we look at point A, it's 4, 2. Go back here, x1 is 4, 2. And if we go to the other point, B, 9, 3. And if we go back, 9, 3. I apologize if this is like, going into too much detail, but I do think it is important to go over it. If you don't really need this much help, you can always just feel free to skip forward. So anyway, so average rate of change. Okay, so let's just plug in everything. So y2 we said was 3. Y1 we said was 2. And then x2, right? So 9. And then x1 is minus 4. And so you should get a slope, right? So 3 minus 2 is 1, and then 9 minus 4 is 5. So our average rate of change is 1/5. And that's the answer. And if we go back to our graph, where is it? Right here. Unfortunately, it doesn't tell me the slope of this line, but like we can just double check. Y equals 1/5 x. And, you know, if I push this up, I don't know, by 2. Maybe not so far. Okay, I mean, we can see, like, pretty clearly. These should be parallel. And it looks good, so. Yeah. So that's number 1. Find the average rate of change with respect to x over this interval from 4 to 9. Okay, so let's move on to number B. Find the average rate of change of f of x with respect to x over this interval from x, comma, x plus h. So, you know, when you look at this problem, well, you know, this is my strategy with lots of math problems. Is I take this. I mean, it might not be that jargony, but you know, math can be pretty jargony, and I change its jargon into like words that I know. So, right, find the average rate of change. Well, that's the same formula from last time. Y2 minus y1, x2 minus x1. And with respect over the interval x, comma, x plus h. So it's very similar to the first problem, right? But instead of like, well, the only difference is that instead of like the interval being defined from 4 to 9, the interval is now more abstract. But like, what does this really mean, you know? So if we go back to, you know, if we drew another number line, you know, and this is 0, and this is 1. And let's say this is our point x. You know, and it doesn't have to be positive. Like, the whole point about being variables is that it can be any number. But let's just say it was somewhere here. So this is x, right? But what does x plus h look like? Well, I don't exactly know what h is, but I know it's like at least somewhere to the right. This will be x plus h. And so that means this distance is h distance away. So if we go back to our previous problem, I already erased it, but you know, it was like 3, 4, ... and then 9. Well, this distance is from 4 to 9. This distance is 5, right? So if you like map this situation onto here, well, this is our x. This is our x plus h. And if x is equal to 4, that means x plus h is equal to 9, and therefore h is like 5. So, like, just because you see variables doesn't mean it's like, you know, necessarily scary. It's just like, instead of working with like, you know, more concrete numbers where it's very, like, I can't apply this to other problems other than the one that's right in front of me right now, I can apply it to lots of different problems. So anyway, yeah, let's just plug it in. So y is still root x. So let's say x2 is the second one. So that'll be x plus h. And then x1 is just x, because this is the first one, this is x1. And so that means y2 will be equal to the root of x2, which is equal to root x plus h. And so y1 will equal to root x1, which is root x. And now we can just plug everything into our formula. So the average rate of change will be equal to, so y2 is root x plus h minus root x all over x2 minus, so it's x plus h minus x. Okay, and now we can, let's see, this x and this goes away because this is like plus x. So plus x minus x, that's 0. So you just got left with h on the bottom. And yeah, I'll just copy paste that over. And that should be our answer. Yeah, there's not much. I mean, like you could try multiplying by the conjugate here, but I don't think it's worth it. I think this is solved enough. Okay, let's go on to C. Use the limit definition of the derivative. Find f prime of x. Okay. Let's see. Limit definition of the derivative. This is one of those formulas that we should know. So, limit definition of the derivative. What is that? So it's going to be equal to, it's going to be the limit as h approaches 0 of this function of x plus h minus function of x all over h. Well, I mean, if you noticed, we kind of already did the work up here, right? So this is technically function x plus h, and this is minus function x, where f of x is equal to root x. And then, well, I mean, h is h, so it's just right there. But let's assume that like we didn't already do this work, so let's just plug in everything. So limit h approaches 0 of, so f of x is still equal to root x because this is still question 1. So what's function of x plus h? Well, function x plus h, every time whatever's in the parentheses, I plug in every time I see an x. So this will be root x plus h. So this will be root x plus h, and then minus function of x. Well, function of x is right here, so minus root x. And the whole thing is over. H. Okay, so here's the problem, right? Because first thing I always try with limits is just like plug in whatever the limit is set to. So in this case, h approaches 0. But like if I set this to 0, then I get a problem of something over a 0. And I can't divide by 0. And so there's an issue. But like it's not the end of the world because we can manipulate this using algebra so that we can get rid of this h in the bottom. But like, how do we do that? So the thing is about, square roots. What's that telling me to do is to multiply by the conjugate. And so the conjugate, right? So if this is like a minus b, and this is a, so the conjugate, if you have two terms, if it's like a minus b, then the conjugate will be a plus b. And the reason why this is useful is, well, let's see what happens when you multiply this out, when you FOIL it out. So the first term will be a squared, and the second term will be plus ab, and then the third term will be negative ba, or I can write it as minus ab, and then the last term will be minus b squared. And what's cool is that the middle terms go away, and I get left with a squared minus b squared. So I mean, like, why is this useful? Well, if you look at our a right here, this whole thing. If you look at this whole thing, and we call that a, and you call this b, well then a squared will be root x plus h quantity squared. And when you have, like, even if it is two terms and they're both being square rooted, well, it doesn't matter how many terms you have. If the whole thing's being squared and they're all under a square root, then the square root and the square interact so that they cancel, and you just get left with x plus h. And if you look at b squared, root x squared, well, that's just x. Okay. So, yeah. Let me just copy this down here. Multiply by the conjugate. So what is the conjugate here? It'll be x plus h plus x, or plus root x, and the thing is about multiplying by the conjugate is that you have to also multiply the bottom of the digit, the denominator, also by the conjugate, because, well, if you think about it, this is technically 1, right? Because it's something, I don't really know what this is, but like this is some amount divided by the same amount. So the same thing divided by the same thing will always equal 1, no matter what. And when you multiply by 1, it doesn't change its value. So that's why it's important to make sure that you're multiplying the denominator also by the conjugate, so that you keep things consistent. So limit as h approaches 0. I mean, you could FOIL everything out on top, but like we already did the work here. So there's no shame in using the formula if it saves you time. So let's see. A squared, what we said is right here, x plus h. Then minus b squared minus x. Okay, and then the bottom, well, that's h times x plus h plus root x. And so, let's see, this is plus x, so the plus x minus x go away, and you get limit h approaches 0 of h over h x plus h plus root x. And so these h's go away. And that was the problem we had at the start. Remember, like if you plug in h approaches 0 here, you get an issue, but we got rid of the h here. So now we should be able to take its limit, no problem. So if I take the limit as h approaches 0, I should get 1 over root x plus 0 plus root x. And you should get equals 1 over 2 root x. And that's our answer. So, right, so this is using the limit definition of the derivative. Just to double check, we know how to take the derivative of stuff without having to use the definition anymore. So y equals root x, right? Well, we know that's x to the 1/2. And this is I believe this is power rule, right? So if I want to take its derivative, I move the exponent in front, and then I subtract 1 from the exponent. So that's 1/2 minus 1. And so that will equal to 1/2 x to the, let's see, 1/2 minus 1, that's negative 1/2. And then, well, whenever I have a negative exponent, I move it into the denominator. So that's 1 over 2 x to the 1/2. And x to the 1/2, well, that's the same thing as root x. And these are the same. And so we know that we did our work right. So that's part C. Okay, on the graph below, sketch a function with the following characteristics. F at 3 is 0. F is continuous on its domain, which is negative infinity to 5, union 5 to infinity. Limit of as x approaches infinity, function of x is negative 2. Limit as x approaches negative infinity, function of x is negative 2. And limit as x approaches 5, function of x is infinity. So, I mean, this is like, a lot of information to take all at once. And so, yeah, let's just break it down piece by piece. So it wants us to sketch a function with these characteristics. So let's list out what these characteristics are. So f at 3 is 0. Okay, what does that mean? Well, I mean, what I like to think of this is like function of x that's equal to y, right? And so this is my x and this is my y. So that means x, y. Well, what's the point? Well, it's 3, 0. So the first characteristic is that I have a point at 3, 0. So it's a very tiny graph, but 3, 0 should be okay. All right, so what's the next characteristic? Well, f is continuous on its domain, which is negative infinity to 5, union 5, infinity. So let's see, f is continuous on this domain. So what does that mean? I think I've also had students get confused on this notation as well. So negative infinity, 5, union, capital U, 5 to infinity. And one thing mathematicians really like to do is condense a lot of information into just as few characters as possible. So what does this mean? Well, this means every number except for 5 is in the domain, basically. Another thing I've had a student ask me about is, what does this U mean? I like to think of it as like kind of like glue. I can stick two different intervals together to just, it's kind of like and. So you can think of it just like, this is like and. So negative infinity to 5 and 5 to infinity. So basically this means every number except for 5 is in the domain. Whoops, where am I? There we go. So every number except for 5 is in the domain. I don't think that's enough information to like concretely draw anything on the graph. Yeah, because it says it's continuous. Oh, that's another thing. What does continuous mean? What does continuous mean? So what does continuous mean? In the context of drawing graphs and stuff, continuity just means that like I can draw lifting my pencil. And that's pretty much, I mean, there's a more technical definition, But I think in the context of this problem, the more technical definition doesn't really matter. Where it does matter is like with more algebraic usages of limits and stuff. But in this problem, what does continuous mean? It just means I can draw the graph without lifting my pencil. And then it says for every number except for 5. So it means I can draw the graph from negative infinity to 5 fine, like without having to lift my pencil. And then once I hit 5, I have to lift my pencil, and then I can get past 5 and I can continue on towards positive infinity without ever having to lift my pencil. So that's what this little sentence means. Okay, so the next section is limit as x approaches infinity, function x is -2. And so what does this mean? All right, so it's limit as x approaches positive infinity. So for when my x values get very large towards positive infinity, if I plug in like, a million, my y value will just be -2. And so if you think about it, like, if I plug in 1,000,000, I get -2. If I plug in 10 billion, I get -2. So this should be, it's just it's a horizontal asymptote at -2. I don't know about negative infinity yet because all it says is positive infinity. So I can't say anything about the left side of the graph, but for the right side of the graph, I know for sure that as x values get larger and larger, my y value approaches but never quite touches -2. Okay, and let's look at the next section. Limit. We have limit as x approaches, okay, there we go, negative infinity of the function is also -2. Okay, cool. So using the same logic, if I plug in very, very large negative numbers, I will also get -2. So that means I have a horizontal asymptote at -2 as well. Let me see. So this one's done, this one's done. Okay. The last one is limit as x approaches 5 is positive infinity. So what does this mean? Well, if I plug in 5, I get a very large number. Well, not 5, because I think 5 is not defined. But if I plug in, like, let's say, function of 4.99, I should get something large. And similarly, function of 5.01, I should also get something very large. And so in the context of this graph, what does that mean? Well, I have a vertical asymptote at 5. Okay, I think that's enough information to try and draw something. So let's see. Okay, so we know that we're here, right? So that's a good starting place. And that as we get closer and closer to 5, we get very large y values. So it should look something like this. As we get large negative values, we get closer and closer to -2. So it should look something like that. And then as we get closer and closer in 5 from the left, we also get very large y values. So it should look something like that. And as we plug in very large x values, we get closer and closer to -2. So you get a graph that's something that probably looks like this. And so that's number 2. The game plan, I mean, I guess this applies to like lots of math, but basically like decode all this jargon into stuff that makes sense for you. And that makes problems infinitely more approachable because it's like I don't think anyone can read this text in one go and just be like, I know what this is saying. So yeah, just take your time with these problems and yeah. Okay, so let's move on to number 3. Okay, find the limits, show work, or briefly explain your reasoning. Okay, so I think in my session when I went over this problem, I did run into an issue, but I think I will go over this problem the way I would do it. I might be doing it wrong because I don't think I was able to find the answer. But I think the more important thing is that we, employ the same kind of strategy for problems of this structure. So, as a heads up, I don't have an answer for this problem. I'm sure if you plugged it into Google, it would give you an answer, but I personally don't have one. But I'll still do it and show you my thought process. So 3a, we have limit as x approaches -1 of the square root of x squared plus 3 minus 5 all over x plus 1. Okay, so with like all limit problems, the first thing I tried to do is to plug it in and see what happens. Unfortunately, if I do that, I get something divided by 0. But just for completion's sake, let's see what happens on the top as well. So I get -1 squared plus 3 rooted minus 5 all over 0, which is, see, this was 1, so this is 4, so root 4, that's 2, so 2 minus 3, or sorry, 2 minus 5, which is -3 over 0. So unfortunately, because it's not 0 over 0, we can't use L'Hopital, I think. Let me do some Googling. Yeah, okay. So when can you use, we can apply L'Hopital's rule, also common L'Hospital's rule, whenever direct substitution of a limit yields an indeterminate form. These forms are 0 over 0, infinity over infinity. Then you can do this thing. So unfortunately, we can't use L'Hopital's rule. So let's try some, algebra to see what happens. So just like before, so we have limit x approaches -1, x squared plus 3 minus 5 all over x plus 1. Whenever you see a radical or a root, a square root, you can try multiplying by the conjugate, see if that works. So x squared plus 3, so plus 5. Same thing on the bottom. Okay. And so, let's see. This will be, no more square root, x squared plus 3 minus 25. X plus 1. Limit x approaches -1. So the top will simplify to x squared minus 22. And the top and the bottom is still the same. And well, let's see. Like, you could try foiling this out, but I don't think that would solve the problem. So the problem is, like, if I still plug in -1, I still get 0, and then 0 times something, right? And then I still get something, you know, something on top divided by 0, which doesn't solve our problem. And I think if you distributed it out, you'd still get the same thing, but let's see what happens. Like, I mean, you can obviously do this by hand, but I am lazy, so. Okay. Okay, so is there a plug-in calculator? I mean, I guess I could just plug it into a graphing calculator. Yeah. Oh. Doesn't seem to be undefined here. Right? Alright, no, is that x equals -1? Alright, so what's going on at -1? Oh, okay, so at -1 it seems to be 0. Okay. Huh. Maybe distributing does work. I'm not sure why that is, but okay, let's try distributing. Limit x approaches -1, x squared minus 22 all over I see. So this will be x root x squared plus 3 plus 5x plus x squared plus 3 where was I again? Yeah, and then plus 5. Alright, let's try plugging in 1. So, -1 squared, that's 1 minus 22. That is -21. And this is divided by, see, you get -1 times, let's see, so this will be 4. So this will be 2 plus, not plus, minus 5 plus, this will also be 2 plus 5. Okay, and you get -1, -21 over. Oh, okay, so I mean, they do, you get 0. Okay. Okay, so yeah, I wasn't able to solve this one. X squared minus 22. According to the graph, though, at -1 it should be 0. But I wouldn't be able to tell you why. Yeah. Sorry about that. But yeah. Alright, so let's try 3b. Okay. So with lots of limit problems, the first thing I try is plugging it in. So you have limit x approaches infinity of 2 over x. So first thing I do is plug it in. You get 2 over infinity. And well, lots of students I think get confused about this as well. Like what's 2 over infinity? What's anything over infinity actually? So 2 over infinity is 0. Anything over infinity is 0 actually. Anything except for infinity over infinity, which is undetermined. But in this case, it's just 2 over infinity. And so why is that? Well, like if you think about it, every time you see infinity, you can just plug in a large number. So let's see what happens when I plug in 1,000. So that's going to be 0.02, right? Which is very close to 0. Like 1,000 isn't even that large if you think about it. So like 2 over a million. It's going to be 0.000 0. Zero. Whatever. 0. Very, very close to 0. And so, infinity is a lot larger than a million. And at a million, we're already pretty close to 0. So any constant divided by infinity will just be 0. And, this is just a, kind of a, like you could just do this, but like I think in the context of the course, I think it could also be helpful to think about this. So if you can remember limit laws or maybe limit rules, you look at the powers of x. So this is technically x to the 0 over x to the 1. Why is this x to the 0? Well, if x to the 0 is just 1. So 2x to the 0 is 2 times 1, which is still 2. So if you have a constant, one way to think about constants is that it has no powers of x attached to it. And so in the context of limit laws, if you look at the powers in the numerator, and you also look at the powers of x in the denominator. In this case, this one, so 1 is larger than 0, and so our denominator is larger. So therefore, the limit as x approaches infinity of 2 over x should also be 0. So, there's two different ways of thinking about it. I personally like thinking about it like this because I know that 2 over infinity, I guess anything over infinity is 0, but you could also think about it in the context of limit laws where in the powers of x and the denominator is larger, so in that case, the limit will just be 0. So that's two ways of going about 3b. Okay, so let's move on to 3c. Okay. So, like I've said many times before, the first thing I like to do with these problems is try, just see what happens when you plug it in. But since this is the, a math course, we're gonna give you like trick questions. So, plugging in doesn't work most of the time, but sometimes it just works. So anyway, this will just be 0, and this is also 0. And so this is undetermined, just based on what we have so far. So we have to do something to it to see what's going on. So what you could do is you could plug in really small numbers. Right? And you can plug in, for example, so the number is close to 0 from the left. So you could plug in 0.001 or negative 0.001. And so if you think about it, let's see, what do you get? 0.01 over, let's see, absolute value of negative 0.01. And so you get negative 0.01 over the absolute value, so it's 0.01. And you should get, well, it's the same thing over the same thing, so it should be negative 1. And then similarly, if you did the same process with this number, you'll also get negative 1. So that's good evidence that it is negative 1. But I don't think it's good enough in the context of math to say that it is equal to negative 1. Another thing you could do is do this strategy where if you look at the powers... Oh, wait. Never mind. That wouldn't work because this is infinity. This is 0. Let me just see what happens when you graph it. Why is this so slow? Oh, here it is. Okay, this makes a decent amount of sense. So, if we look at what's going on over here, so this is the graph of x over absolute value of x. If you look at what's going on over here, well, if you plug in any number in the x number line, you should get negative 1. Because similarly, if you plug, this is what happens. You plug in a negative number, the negative number stays normal on top, but then the sign gets flipped. So then since the signs don't match anymore and they're being divided, it's the same number being divided by the same number, so you should always get 1. And on the flip side, if you plug in positive numbers, you'll always get the same number divided by the same number, and so you should also always get 1. But this problem is specifically asking for 0 from the left, right? So if you look at 0 from the left, 0 from the left, the limit as x approaches 0 from the left will just be negative 1. If it asks for the limit as x approaches 0 from the right, well, in that case, the answer would be 1. If it asks for the limit as x approaches 0 in general, it would be undefined. So let me write that down. Okay, so limit as x approaches 0 from the left of x over absolute value root x. And so if you were to graph this, right here is negative 1, and up here is positive 1. And so if you were to graph this, you'd get a line that looks like this, sticking out, and you'd also get a line that looks like this. Right? And so, let's see. What is the limit as x approaches 0 from the left? Well, I mean, as it approaches 0, so here is 0. So as we approach 0 from the left, it seems like we're at negative 1. this is -1. And if you approach 0 from the right, you should be at +1. So because of the same logic. However, if you had the question where it was like this, as x approaches 0 in general, it should be undefined. So I guess I got a little off topic, but I mean, I think it's more interesting to look at this problem, in the context of just like the limits from all the limits, because I think it's more useful to think about it like that. Right. So the general strategy, like, if you can't really do any algebra on it, you can always just look at the graph. And if you don't know what the graph looks like, you could always just try plugging in numbers and making a graph yourself. So yeah, so that one's C. All right, so let's try D. So you have the limit as x approaches positive infinity of 7x cubed minus 3x squared plus x minus 6 all over 3x cubed minus 15. And so what is that? So this one is it's not too bad, because the thing that saves us a lot of work and having to think very hard is this positive infinity thing here. And so what this positive infinity is telling me to look at is like end behavior. And so what this is like the limit law question, right? So like if we have x approaches in infinity, what should we be looking at in the context of these problems? The thing you should be looking at are the powers of x. So you have this cubed here and also this cubed here. And this is the largest power of x in the numerator, and this is also the largest power of x in the denominator. And they happen to be equal. So 3 equals 3. Right, and in this case, we look at the coefficients. And we make a ratio of the coefficients. So so this is just 7/3. And that's it. If we look at the graph, hopefully it might make some sense. So let's try plotting it. Okay, sorry. Let's see. So this is what it looks like. We're interested in positive infinity, right? So if you look at the graph, let me see. Let me plug in y equals 7/3. Okay. And this is the 7/3 is what we came up with, right? That's our yeah. So that's the limit we got. It should be 7/3. So let's see what's going on. Okay, there we go. Right, and it seems like it is approaching it. But like, I guess you can ask, like, the question is, why does it approach 7/3? Why doesn't it blow up toward infinity? Why doesn't it? Like, it seems like if you look at the numerator, right? Like, it seems like it has a lot more terms. Although, I mean, I guess it is being subtracted by 3x squared, but I don't know. And then the bottom seems like, I mean, it is 3x cubed, but then there's a lot of different moving factors, and it's hard to see, like, oh yeah, it's just 7/3. So like, why is this the case? One thing I like to do with limits is just to just plug in the numbers and see what happens. So function of x, right? So let's see if we plug in like 1,000, right? 7 times 1,000 cubed. minus 3 times 1,000 squared plus 1,000 minus 6. And 3 times 1,000 cubed minus 15. And like, I mean, I guess I could continue. So you get 7. What's 1,000 cubed? Well, that's 1,000,000. Wait, no, not even 1,000,000. I think it's larger. It's 1,000,000,000. Right? Because here's one set of 1,000, here's another set of 1,000, and here's 3 sets of 1,000. So it's 1,000,000,000. So it's 7 billion minus 3 times 1,000,000 plus 1,000 minus 6. And this is all over 3 times the same number, 1,000,000. Or no, sorry, 1,000,000,000. The same amount of zeros, yes, and then minus 15. So hopefully by now you can kind of see what's going on, right? Like here we have 7 billion and subtracted by 3 million. I mean, 3 million is kind of a large number, right? But like in the context of a billion, 3 million is only like 1,000th as large, right? So if you could, this is 1,000th as large as this number. And 1,000, like in the context of a billion, like it doesn't matter. And then minus 6, that really doesn't matter. So like, it's like, these are negligible. Negligible, right? And if you look at the denominator, well, same situation, right? So 3 billion minus 15, like what's that? What's minus 15 going to do in the context of, so this is basically 0, right? And so, well, I mean, like, you know, with all fractions, even if there are large numbers, like if you have the same thing on top and you have the same thing on the bottom, they cancel. And so, in the long run, you should just get 7/3 ish. Because like, I mean, it is basically 0, but it's never going to be equal to 7/3. So yeah, in the context of these infinite limits, you look at the powers of x. If they're equal, then it's the ratio of the coefficients. In this case, it's just 7/3. So hopefully that gave you some intuition on why this is the case. Okay, let's go on to E. All right, so we have limit as x approaches negative infinity of the cube root of x minus 5x plus 3 all over 2x plus x to the 2/3 minus 4. Okay, so the thing I'm looking at here is this negative infinity thing here. And the negative infinity thing is telling me, oh, it's probably the same strategy as up here. It's the you know, look at the powers of x and go from there. Right, so let me rewrite this so that it's probably a little bit more maybe like palatable. So the x, cube root of x, that's the same thing as x to the 1/3 minus 5x. I guess I can write that as 1 plus 3 all over. This is 2x to the first power plus x to the 2/3 power minus 4. And so what is the largest power of x I have here? It's going to be this number and this number, right? Okay, and they happen to be equal again, so the answer should be negative 5/2. Yeah, so not too bad, not too bad. Yeah, you could say the same thing like you can plug in very large numbers and this same situation will still play out, even though, the exponents are, not quite so linear, but, you could try that yourself if you're interested. Okay, so let's move on to number 4. Okay. For the graphs below, find the x values for which a function of x is continuous. And label and categorize the type of each discontinuity as removable, jump, oscillating, or infinite. Okay, so, right. Let's look at the key little sentence fragments that are important here. So find the x values for which function of x is continuous. So in the context of this problem, and it's another graphing problem, right? What's important to me here is not necessarily the technical term of what continuity is, but what's important here is, can I draw this without lifting my pencil? And label and categorize the type of each discontinuity as removable, jump, oscillating, or infinite. So categorize the type as these. So let's look at the first one. I guess the easy one is to label and categorize the type of each discontinuity first, and then we can look at like which specific x values is it discontinuous or is continuous. So let's see. If we look at this one, what's the type of discontinuity? Well, in my head, it's oscillating. Why is, I guess you could ask the question, why is an oscillating function discontinuous even though you technically never lifted your pencil, right? Because I can imagine like if you had an infinite number of time, you could just keep drawing the same scribble back and forth, back and forth, back and forth. And then eventually, after an infinite number of time, you go on and forth, right? So technically, I did draw it without lifting my pencil, right? But it's like, actually, I don't think I could answer that question because, that's interesting. But anyway, I mean, let's look at 1 over x. All right, so let's look at function x equals sine of 1 over x. Okay. So what I like to do when you have two functions composed of each other, right? So you have sine of x, this is the outer, and you have 1 over x, and this is the inner function. What I like to do is I like to look at like, okay, I have to analyze what is 1 over x doing, and then what is sine over x also doing, and then like maybe if I take the output of the inner function and I plug it into the if I take the output of the inner function and I plug it into the outer function, like what does that look like also? So like I know like on a test like you guys won't be able to use a graphing calculator, but like just for future reference. So what is 1 over x doing? Right. So if you plug in, let's say 1, you'll get 1 over 1, which is just 1. And if you plug in 2, you get 1/2, which is 0.5. And so this makes sense, right? So as the numbers get larger and larger, the larger numbers you plug in, you get the reciprocal, and those reciprocals will get really close to 0. However, what's interesting here in the context of sine x is like the numbers that are really close to 0, but not quite 0, like what's happening to the numbers? Well, I mean, they blow up to infinity. Like, what is, if I plug in a half, right, it should be 2. If I plug in a quarter, 0.25, I should get, 8. Right, so here, I'm at 8. So the smaller numbers I plug in, I should get very large numbers on the output. And then similarly for the negatives, I get a similar situation, except it's just, below the x-axis. And so that's 1 over x. Let's look at sine of x. Right, and like, what happens when I plug in, like, let's say sine of ax, right? Is it? Why isn't it giving me? Okay, there we go. This is the one I imagined. Huh. Okay, I don't think this is quite working. Okay, there we go. All right, there we go. All right, so let me slow this down a little bit. Okay, so as a is very, with smaller a values, it's kind of like stretching and like squeezing a spring or something. So when a is large, or I guess negative. Okay, when the large values of a, so when it's greater than 1, my sine wave gets like smushed, right? And then when a is less than 1 and really close to 0, my sine gets really stretched out. Right? And so what happens, like, why is this important? Well, 1 over x, right? It's kind of doing both at the same time, right? If you go out towards here, my sine is like, see, if we look at 1 over x, right? If we look at 1 over x, well, if I plug in, let's see, my y values of sine 1 over x is really close to 0, and sine of small numbers makes the sine get really stretched out. And then if I plug in really large numbers into sine, and not large numbers, but like numbers that change really rapidly, I should get a very, very squished graph of sine. And at the extreme, right, so sine of infinity, or let's see, sine of 1 over x is like, sine of 1 over x, where x approaches 0, well, that's kind of similar to sine of like a large number. So anyway, right. So if we go back to the problem, let's see, what is this? This should be an oscillating discontinuity. But where is it? The first part of the problem, find the x values for which function of x continuous. Okay, so I guess you could flip the question around. Where is sine 1 over x discontinuous? And so, like, sine of x, right? We look at that. sine of x has no issues. Like, it's defined everywhere. Yeah, so there's no issues with sine of x. So sine of x has no issues. But if you plug in, say 1 over x, oh my god. If you plug in 1 over x, the only issue is x can't be 0, right? Because you get this vertical asymptote. So if you plug in, right? So sine of x is fine. Like it behaves. 1 over x is that x cannot be equal to 0. So sine of 1 over x, like if you plug in 0, sine of 1 over x also doesn't know how to handle that issue. So it's like sine of like undefined. Right? So it's like it doesn't really make sense to plug in 0 into sine of 1 over x. So therefore, sine of 1 over x kind of inherits 1 over x's like problems. So basically, where is sine of x discontinuous? So x can't be 0. And that's it. So find the values for which f of x is continuous. That will be from, if you wanted to write in a domain, negative infinity to 0, a union 0 to infinity. And then for b, all right, what is b? Well, it's some sort of a step function, right? So find, or let's label it. I think it is a jump discontinuity. Right? And then let's see. We have to, right, where is it continuous? Well, it's continuous, so if you look closely, it's continuous from every number. So if you look at this range, right, so from 4 to negative 3, it will be continuous for every number between 4 and negative 3, but not necessarily at negative 3 or 4. And if you continue that pattern, it won't be continuous at negative 2 or negative 1 or 0. So basically, every number except for the integers. And that should be the answer. Anyway. So number 5, find the values of a that make function of x this, what is it called? Can't exactly remember what these are called, but composite functions maybe? No, I don't think that's right. Anyway, the function that where if it's like x is greater than 2, it's this, and x is less than 2, it's just 12. I think lots of students also had problems with this question too, but okay, so let's go over it. So a function of x equals to a squared x minus 2a, where x is greater than or equal to 2, and you have 12, and its x is less than 2. So you have two types of functions here, and the only thing that makes one over the other is that your x value, like it's only this when your x value is greater than 2, and it's only 12 when your x value is less than 2. So like, how do I, let's start with like the easier part, right? So it's like, what is 12? Right, so this is y equals 12. Assuming that x is greater than 2. What does that look like? So y equals 12, right? So 12's here. And then x is less than 2. So let's say 2 is right here. So what does y equals 12 look like? Well, y equals 12 will look like this. I should probably use a different color line. There you go. So y equals 12 looks like this. It's just a straight horizontal line. Another way to think of it is like this is the line where all values of y is 12, if that helps. Okay, so that was not too bad, but let's see, what does what does this one look like? A squared x minus 2a. Well, like a is just a number, like sure it's a variable, but it doesn't affect our graph. I mean, it does affect our graph, but it doesn't affect like the overall shape of our graph. What does affect the shape of our graph is this x right here, right? And this is x to the first power. So x to the first power is always going to be linear, no matter what. Oh my gosh. No matter what. Yeah, no matter what, no matter what value of a. And so, like, sure, a moves the graph around, but like this x to the first power means it's going to be a straight line, some sort of straight line, and it depends on what a value is, and that a value will move the x around so that, well, I mean, it could be anywhere, but in this case, we want it to be continuous. Oh, okay, so here's some more notation that could be confusing. Continuous here, so let's see, let's look at, what does upside down a mean again? Sorry. Okay. It means for all instances. Okay. So here is very shorthand notation that says, and then I think this means such that, and then what is this? What does this R mean? That means all real numbers. Okay, so find values of a that make this function continuous for all instances of x such that all real numbers, I guess, like work. Right? And like I think also students got confused on this notation. So yeah, all this is saying is that what values of x will make this continuous everywhere, and that's it. Yeah. So anyway. Right, so let's look at like the mechanics of, this guy, right? This a squared x minus 2a, like what does that even look like? All right, so just like I said, a squared x minus 2a is going to be a line, no matter what value of a. So if I move this around, it does this weird, like, if I vary what a is, like, it's always going to be a line no matter what. Like, it'll move around, but it's always just going to be a line. So, I guess that now the trick is just like, well, okay, well, how do I find which value of a will make this true, right? And so, like geometrically it's hard, but like algebraically it's not too bad. So let's try doing, some stuff. All right, so we have a squared x minus 2a, right? And this is function of x. Sorry. Let me try plugging in 2 here, right? Because like these functions are always going to be continuous, but the problem is like at 2, they're not necessarily going to line up. Right, so let me plug in y equals 12. And then x equals 2. Right, and so the question is like, I want an a value such that this red line will hit the orange line at this spot right here, 2, 12. And so the only thing I'm allowed to move is this a value. Oh, let's see, like it's somewhere. A is somewhere around here. Like, I mean, you wouldn't be able to know that, but like, see, like, I need to move this a value around such that the intersection is continuous, right? So anyway, how would I do that? Well, let's see. I know that f at 2 is, okay, so f exactly at 2. Well, x is greater than or equal to 2, so at 2 I should be using this function. A squared times 2 minus 2a. And we can calculate that, right? So that's 2a squared minus 2a. Well, in order for it to be continuous, right, I have to equal it to something, right? And the thing that would make it continuous is that I should be set it equal to 12. And why does this make sense? Well, if you think about it, like, these are all y values. And so it makes sense that, like, if they're both equal, if I plug in the same x, I should get y values that are the same, right? So I don't know what a is, but I should, if I set it equal to 12, I should be able to get the a value that will work for me. So anyway, I can factor out a 2, and then I can divide the 2, so you get 6. And this is a quadratic equation, so I'll just move everything to one side, set it equal to 0. I can factor. 6 has factors of 6 and 1, 2 and 3. Since this is negative a, this one is probably negative 3, positive 2. So a plus 2, a minus 3. And that's equal to 0. So that means a equals negative 2, or a equals 3. And those are the values of a that make this continuous. And let's see what's going on. So we said a equals negative 2. Right, so it's continuous, right? So we want these lines to intersect here, right? Yeah, looks good. And then we can plug in 3. Also looks good. And if we, move any other value, at least in the range from negative 5 to 5, doesn't seem to work. Except for, yeah, so it seems like this is good. I had a student ask me, are these the only numbers that'll work? Yes, these are the only numbers that'll work. I couldn't give you more justification other than the fact that the equation that gives you the answer, 2a squared minus 2a, well, there's a theorem that says, like, there's only going to be the same amount of solutions as the powers of the variable that you're dealing with. So since it's a squared, there's only going to be two answers. So okay, let's look at 6. I think, yeah, I should make this much larger so it could be easier to see the graph. So the graph of f prime, and f double prime are shown below. Identify each curve and give a brief explanation to your choices. Okay. So, we have f prime, and f double prime. And so what does this mean? So this is the original function. This is the derivative. Of the original function. And this is the derivative. I can't write right now. Derivative of the derivative, right? And that could be kind of confusing to, like, figure out just by looking at it. But like, just look at, all right, so when I look at these problems, the first thing I look for are maximums and minimums. I look at the peaks. So here's a peak, here's another peak, here is another peak. Seems like there's a peak here too. And the reason why that's important is that when you look at the peaks, right? So let's look at B specifically. The slope at the peak or minimum, like also down here too. Oh my gosh. The peak at the minimum is also, well, what's the slope of these lines? Well, the derivative is just 0. Also down here, the derivative is also just 0. And so you need to look at the corresponding graphs and see which of these graphs, when my original function is 0, or when my derivative is 0, has the y value also 0 at that point. So, I mean, it looks like we kind of stumbled onto one already. Based on this, I know that, so B, like B is the original function, probably, well, maybe not, but like, I know that the B derivative is equal to C. Yeah. So that's one chunk of information. Let's look at C. Well, the derivative here, I mean, I don't really see, yeah, so C has no derivative here. So, I don't know. Let's look at this peak, right? And let me see. If we plop a point down, oh, it looks like B. Okay, so that's good evidence. Oops, sorry. It's good evidence that A prime is equal to B. Maybe we could find more evidence. I mean, I think like we're good to stop here, but I think it could be good to just look at a little bit more bits of information. All right, maybe there's another piece of information that can tell us maybe more about C. So I'm looking at the peak of C right here. If we plop down a point, I mean, kind of doesn't line up exactly. I'm not sure. Yeah. So, oh my gosh. Other than just looking at peaks, you can just look at the slopes in general and see like where does it line up. So if we look at, all right, so let's try to organize this, these little statements we have into something that makes a little bit more sense in the context of this question. Oh my goodness. Okay, there we go. Please. I hate this. Okay. I'll just write it down here. Right, so B prime equals C, and A of A prime equals B. So if A is our original function, So if f equals a, then f prime is equal to a prime, and we said that was b. And if f double prime, that's equal to a double double prime, which is the same thing as b prime, which we said is right here. So c. So I think we have the answer here, right? So we have f equals a, f prime equals b, and f double prime equals c. And let's just see, like, more information to see if this makes sense. So if a is the original function, if we look at the slopes of a, if I were to draw a straight, a tangent line here, the tangent line at this point seems to be, pretty positive. I feel like at B it's also positive, and if you also look at C, it also seems to be positive. If you draw a tangent line here, oh my gosh, what a bad color. If you draw a tangent line here, you should get a negative slope. And we said B was our derivative, right? So it should be a little negative, but not very negative. It seems like that checks out too. Yeah, so I mean, I've convinced myself that this is the case, so. Okay. Okay. Let's move on to 7. We're going to differentiate the given function. So function of x is equal to 9x squared minus 2x plus 4. Okay, so how do I differentiate? What does that mean? Differentiate is like, I like to think of it, it's kind of, it's like a verb. Basically, that's how I like to think of it. Differentiate the given function means take the derivative of the given function, if that confused you. So anyway, the function is 9x squared minus 2x plus 4. So, like, how do I take this derivative? Well, if you have lots of terms, you take the derivative, where am I? You take the derivative of each term one by one. Okay? So, what's the derivative of 9x squared? Well, this is power rule. And if you remember what you do, one thing that might help is you can leave the coefficients out of it. Coefficients don't change the derivative too much. So you could just factor out the 9 and you can take the derivative of x squared. So with the power rule, what you do is you move the exponent to the front, right? So it's 2x, and then you subtract 1 from the exponent, so 2 minus 1. And then minus, okay. Like before, you can leave the coefficient out of it, and you can just take the derivative. So that's just 2. And then what's the derivative of x? One thing that might help with this, it might not be too obvious, but this is technically x to the first power. And since it's an x with a power, you can use the power rule again. Right? And so you can bring the 1 in front. So that's 1x. And then 1 minus 1. Right? And then plus, okay. So it's like, okay, how do I take the derivative of a constant? Well, it turns out the derivative of a constant is just 0. I can justify that for you as well. So why is the derivative of a constant 0? Right? If we use the problem's example, it's just 4, right? And so this is what the graph of y equals 4 looks like. So it's the derivative of y equals 4? Well, we know that derivative is the slope at each like point in the graph, right? So what's the slope of this line? Well, the slope is just 0 everywhere. So the slope of 4 is just 0. And it doesn't have to just be 4. It can be any number. It could be 5. Any number will just give you a straight line, a horizontal straight line, right? And so the derivative of a constant is just 0. Okay, so this will be 9 to, so x2 minus 1, that's x to the first power, minus 2 times 1, x to the 1 minus 1, that's x to the 0. And so 9 times 2, that's 18, x minus 2. Okay, so what's x to the 0? X to the 0 is just 1. In fact, anything to the 0 is just 1. The only exception is 0 to the 0, which is undefined. Right, and so you get 18x minus 2, and that should be our answer. Why is anything to the 0, 1? Well, let's look at powers of 2, right? So we have 2, 2 to the 1, 2 squared, 2 cubed. So 2 to the 1, well, that's just one copy of 2, right? So that's 2. And then 2 squared, that's 2 times 2, which is 4. And then 2 cubed, that's 2 times 2 times 2, which is 8. So I think everyone is fine going up this way. How do I go backwards? Let's say I started at 2 cubed and I want to go down to 2 squared. Well, how do I get there? I take away 1 power of 2. So I divide by 2. And so the difference between 2 cubed and 2 squared is that I have 1 less power, 1 less copy of 2 being multiplied. And then I can repeat the pattern, right? I can go back by dividing by 2. So the difference between 2 squared and 2 to the first power is a copy of 2. What do I do if I want to keep continuing the pattern, right? What's 2 to the 0? Well, that's 2 divided by 2, which is just 1. And you can see that if I plug in any number, it doesn't even have to be 2. I'm going to be dividing by that same number, and that number divided by itself will always be 1. And then, if you continue the pattern, what's 2 to the negative 1? I divide by 2 again, right? So 1 divided by 2, that's 1/2. And if I continue the pattern, divide by 2 again, 2 to the negative 2, that's 1 over 2 times 2, which is 1/4. And so here's also an explanation of why negative exponents make it so that you get the reciprocal of the power. So anyway, that's a side note. Right. Let's go on to B. 5. Okay, so y equals to 5 times the cube root of x. Okay, so this is a little confusing, right? Because I don't think we have any rules about cube roots or square roots or just roots in general. But this is really just a subset, right? You can just use the power rule here. But how do you do that? Well, if you can remember, cube root of x is the same thing as x to the 1/3 power, right? And so y prime will just be, well, I'll leave the 5 out of it and I can handle it later. I move the 1/3 in front, x, and then I subtract 1. So 1/3 minus 1. Okay, and then I can deal with the coefficient now. So that's 5/3 x to the, so 1/3 minus 1. So that's 3 over 3, which is negative 2/3. Right, and then I can simplify this even more. That's 5/3. Okay, so since it's negative, I can bring it down to the exponent. Not the exponent, to the denominator. 2/3. And then I can rewrite this as 3x to the x squared, and then cube root. I think this is probably the preferred answer. Technically you're done with the calculus here, or I guess here, right? 5/3 x to the negative 2/3. Like, that's not wrong. It's just not, I think lots of math people prefer that, like, you're given the answer back into the form you started with. So that's why I went through all the extra work too, right? Because I had a cube root, and I preferred to have the answer back into the cube root form as well. But I mean, like, technically you're done here as well, right here. So, yeah. Okay, so now I have C. So I have y equals 1 plus 1 over t. So let's see. When you have, lots of terms again, you take the derivative of each thing one by one. So y prime is equal to, okay, so what's the derivative of 1? Like I said before, the derivative of a constant is just 0. And so what's the derivative of 1 plus t? Well, again, this is also just a subset of the power rule, right? And why is that? Well, if you rewrite this, that's 1 plus t to the negative 1. Right, so that's going to be plus. And so I bring the negative 1 in front, negative, and then I, subtract 1 from the power. So negative 1 minus 1. And so you'll get negative t to the negative 2. And then, just like before, we want to rewrite the answer in terms of, like, kind of what we started with. So we have negative 1 over t squared. That's the answer. Okay, and now we're dealing with d. V of u is equal to negative 5 EU. So V, I do not like that. VU is equal to negative 5e to the u. So I guess, like, maybe some students might get confused with this notation as well. If it helps, you could just rewrite it like this. Function of x is equal to negative 5e to the x. I don't think students will get confused about this, but yeah, you don't have to if you don't want to, but it might help. Right, so how do we take this derivative? So v prime u, well, that's going to be, whenever you have a coefficient, you can just leave it out in front and deal with it later. What's the derivative of e to the u? Or if you prefer, e to the x. So what's the derivative of e to the x? Well, it turns out that the derivative of e to the u is just itself. So you get negative 5e to the u. Why is the derivative of e to the u just itself? Well, if you can remember this rule, b to the x the derivative of b to the x. Well, if you can remember that, the derivative of b to the x is b to the x ln b. Right, and b is just a number. All right, and let's say we plugged in 2 d dx of 2 to the x. That's 2 to the x ln 2, right? And just like 2, e is also just a number. E is about 2.71 something. So what happens if we plug in e to the x into this formula? Well, you'd get e to the x ln e. And so, like, if you can remember the properties of natural logs, and if you plug in e into it, this is technically natural log e to the 1. And when you have e to some power, the e and the natural log will cancel, and you just get left with 1. And so you just get left with e to the x times 1. So the derivative of e to the x is just itself. So, yeah. Also, that brings up a side note, like, I think lots of students get confused with b to the x versus, I guess, to be more concrete, they get confused with 2 to the x versus x squared. I mean, they might look similar, but these are completely different things, and we need to treat them differently. So 2 to the x, right, is an exponential function. One way to think about it is like for every value of x I go up, I double where I was before. So at 1 I started at 2, at 2 I get up to 4, at 3 I double again, I go up to 8, and then so on and so on. X squared is completely different. For every value of x, I square it, right? So at 1 I'm at 1, at 2 I'm at 4. Well, I mean, lots of people are familiar with parabolas, but these are very completely different functions, and we need to treat them differently. Lots of students might be tempted to do this. They'll say this. So they'll use the power rule, right? So they'll bring the x in front, 2 to the x minus 1. This is wrong. Yeah, make sure that you do not use this on this. These are completely different things. Okay, find the derivatives of the function, simplify your answer. Okay, so function of x equals negative 3x over tangent x. And what does this look like? Well, this is a quotient rule, right? So, see, what is quotient rule? So f over g derivative is equal to f, so low d high, right? So it's g f prime minus high d low, so f g prime all over g squared. Right, and we can just, if it helps, you could maybe list out what everything is. So if f is negative 3x, f prime is, just like before, if you don't want to deal with the coefficient yet, you can just leave it out on the front. And, oh, okay, so here is an example of what I was talking about. 3 to the x. People might be tempted to use this rule, but it's actually going to be this formula. So it's going to be 3 to the x ln 3. And then g is the bottom, so that's tangent x. And so g prime, derivative of tangent, is secant squared, I think. Yes, okay. Derivative of tangent is secant squared. And so just put all the pieces together, right? So you have tangent x. F prime was, well, I guess, It's not too. I'll just put the negative in front. 3x natural log times 3 minus, and then f was, I guess it'll be plus now, 3 to the x, and then g prime is secant squared x. And then the whole thing is divided by the bottom squared. And the bottom squared is tangent squared x. Is there any sort of simplification we could do? Secant, let's see, secant, it's the same thing as 1 over cosine. Would that help? And then tangent is the same thing as sine over cosine. Oh, no squares. Same thing as sine over cosine. I don't think it's worth going through all that, so I would call this good. Oh wait, there's B, so let me move this down. Okay, so let's go on to B. So what is B? You have x cubed sine x. And so what is this? This is product rule. Product rule where this is f and this is g. Right, so f times g derivative is equal to the derivative of the first times the second left alone plus the derivative of the second times the first left alone. Yeah, so let's just do that. So it's the derivative of the first, well, that would be 3x squared, and the derivative of the second, the derivative of sine is cosine squared, or just cosine, sorry. Plus, and then g prime, oh, sorry, I made a mistake. Okay, so 3x squared, and then, sorry, the second one left alone, so it's just sine x. Plus, and then g prime, so the derivative of the second, which is cosine x, times f, which is x cubed. And is that good enough? I mean, for me, that's good enough, but I guess you could factor out the x's. So you get x squared 3 sine x plus x cosine x, maybe? Yeah, I mean, yeah, these are probably equivalent, but yeah, that's the answer. Okay, and then for C, arctangent of 2x. What kind of problem is this? Well, this is general, right? I personally don't really like using the U method, where you set something equal to U. I think the inner function equal to U. I mean, you could keep using that method, but maybe if you don't like that method either, maybe this might help you too. So what I like to do is identify the outer function. Right, and so what's the outer function here? In this case, it's going to be arctangent of x. And then the inner function, inner, will just be 2x. Oh yeah, and I think students got confused on what arctangent is. Arctangent and tangent inverse, and also sometimes written like this. These are all the same thing. Yeah. Similarly, arc sine, arc cosine, and then sine inverse, cosine inverse, also the same thing. Yeah, I think I had some students get confused about that. So now that you have identified the outer function and also the inner function, you take the derivative of the outer function and then you plug in what the inner function was. So the derivative of arctangent is 1 over 1 plus x squared. And so the derivative of arctangent of 2x is going to be 1 over 1 plus 2x squared. And then because of chain rule, you also have to multiply by the derivative of the inner function. Derivative of the inner function is just 2. Right, so that's going to be 2 over 1 plus 4x squared. And I don't think there's anything else you can do to simplify that, so that's good. And then d, right? So e to the t divided by t. So how do I handle this? So there's a few ways of going about it. This is like yeah, I think these are the two ways of going about it. You could do chain rule with quotient rule or chain rule with product rule. I think I personally want to do chain rule with product rule because quotient rule tends to be a little more clunky and a little bit more work. So, but how do we rewrite this and so that it can be product rule? Well, you just do this: e to the t times t to the negative 1. Right? And so now we take its derivative. Let me move off to the side a little bit. So e to the t, derivative of that. Okay, so what's that going to be equal to? So just like, let me remind ourselves of the product rule. So that's f prime g plus g prime f. So what is f prime? Well, that's e to the t. I'm going to take the derivative later, and then times g, this is t to the negative 1, plus, and then t to the negative 1 prime times e to the t. Okay, so now we have to handle this. What is the derivative of e to the t? Well, this is chain rule. So let's identify the outer function. So the outer function is going to be e to the t. And so we know the derivative of that, right? It's just e to the... It's going to be e to the... to itself. It's going to be itself. E to the t. And then multiply by the derivative of the inner function, which is going to be e to the t. Okay. And then t to the negative 1, I will rewrite it like it started with, so that would be t. Yeah. And then plus derivative of that, so that would be minus t to the negative 2. And then that's left alone, e to the t. And then I can combine these powers, e to the t plus t all over t. And then I could subtract because of this minus sign, e to the t all over t squared. And I'd call that good. Good enough. Okay, number 9. Find the equation for the tangent to function of x equals to this at the given point, and sketch the curve and tangents together. So find the equation for the tangent to this at the given point and sketch the curve. Okay, so how do we do that? So when it says find the equation for the tangent, I guess you could say step 1 is like find the derivative. Why is that useful? Well, when you find the derivative, it gives you the slope of the tangent, which is like right. So it gives you the slope of the tangent, and for a line you need two parts. You need a slope and a point. And then I guess step 3, put the slope and right. So find its derivative. It gives you the slope, which is a part of the equation that you need, and then probably gives you the point already. Yeah, the point 3,4. You put the slope and point together, and you find the equation of the line using that information. Okay. Right. So what's its derivative? So function of x. Negative x minus 3 squared plus 4. So how do I take its derivative? Okay, so just like before, if you ever have a coefficient in front, you don't have to deal with it till later. This is like chain rule. Well, I mean, it is chain rule. You could also FOIL it out and then find the derivative of each term when you FOIL it out, but I don't think it's necessary. I mean, you could if you want to, but I won't. So the 2 goes in front, and then x minus 3, and then the, subtract 1 from the power, and then times the derivative of the inside. Well, the derivative of the inside is just 1 because derivative of x is 1, and then derivative of 3 is 0. So times 1 plus 0 because derivative of 4 is 0. And you can simplify this out. Negative 2x plus 6. Okay. So we have found the derivative. Okay, so for step 2, we want the slope of the tangent, right? And how do we find the slope of the tangent? Well, you just plug in the x value that you're interested in. So in this case, it's at 0.34, so we plug in 3. So this is negative 6 plus 6, which is 0. So it turns out the slope is 0. Okay. So m equals 0. So now we use, you can use any method you want to find it, but I personally like this method, y equals mx plus b. Then we plug in the point, so 4 equals 0 times 3 plus b. So 4 equals b. So the equation of the line is y equals 4. Right, and find the equation of the tangent to that. And that should be our answer for part A. And then just to double check, let's graph it. So let's graph the original function. Well, I mean, one way to see without having to pull out a graphing calculator is, let's look at right here. Does this look familiar? This is the y equals a x minus h plus k. This is the vertex form of a parabola. And so what's going on at hk? Our vertex is located at hk. And so We don't really need to look at the graph, but let's see. Let's see what's going on at the vertex, right? The vertex, the slope will be flat because it's a minimum or a maximum. In this case, a maximum. And it makes sense that our slope is 0, right? So our slope is 0. It should be at a maximum. Anyway, let's graph it just to see. Anyway. So you have negative x minus 3 quantity squared plus 4. Right? And our vertex is at the point 3, 4. And if we plug in y equals 4, that's our slope, or that's our tangent at the point 3, 4, which makes sense. Right, so part B, where x is 0. Okay, so this might be a little confusing, right? Because let's see, it doesn't kind of fit our steps, right? Because we find the derivative, it gives us the slope of the tangent, but like we need a point, right? But I mean, there's an implicit point, right? There's f at 0, which is, let's see, negative 0 minus 3 squared plus 4, which is, say negative 3 squared, that's negative 9 plus 4, so that's negative 5. So technically, this is 0, negative 5. I've seen, a decent number of students trip up because like, oh, I don't have a point, but whenever you have an x value and a function, you implicitly have the y value as well. So, right, now we still have the derivative, right? So we can just reuse this. So, right, so that guy, right? So f prime at 0 in this case, which is negative 2 times 0 plus 6, which is 0 plus 6, which is just 6. So our slope is 6. So slope equals 6. Our point is at 0, negative 5. And so if we put this all into if we can find the equation of the line using these two pieces of information, y equals mx plus b, so negative 5 equals 6 times 0 plus b. Negative 5 equals, so 6 times 0 is 0, and then, so b equals negative 5. And let's see, then y equals 6x minus 5. And let's see if that's true. So at 0, looks good to me, right? Yeah, looks good to me. Nice. Okay, number 10, find the limit using squeeze theorem. Oh yeah, I forgot to mention, if you're following along and sometimes the questions don't match what was on the midterm, I think this is the updated version of the midterm where the typos are fixed. I think I noticed that some students, they got x squared sine x, which I think is a typo. Yeah. Because, if it was just this, it'd be a lot easier to solve. You can just plug in 0 and you'd get 0, right? Because this would be 0 squared times sine of 0. Sine of 0 is just 0, so you get 0 times 0. And so you don't have to use squeeze theorem anymore. So anyway, so you limit x approaches 0. Let's see. Yeah, x squared sine 1 over x. So that's going to be, okay, so let's plug in 0, right? So you get 0 squared times sine of 1 over 0, which is, not defined. So you can't just plug in. What we can do, and the problem gives us a hint, right? It says use squeeze theorem. So let's try using squeeze theorem. We're given this sine thing, right? So let's start with sine. Why do we want to start with sine? Well, the idea with squeeze theorem is that like we have the thing we're interested in, right? And we want to squeeze it in between two other things where we can find a and we also can find B relatively easily. And if we can find A and we can also find B, and we know that this thing is in between what these two are, we can at least either limit the range down so that we can have an idea of what the answer should be, or we can just find the answer straight up. So, sorry, let me move these down. So, what can give us this sort of structure? Well, sine can offer that for us. And why can it offer it for us? Well, let's look at what sine looks like. Let's see, if I zoom in really close on sine, right? Notice the y values. It goes from positive, I guess it goes from -1 to +1, right? And it never goes above or below those y values. And that is our range. And so we can say that sine never is below -1 and is never above 1. So we're given this sort of structure right off the bat, which is really nice with sine and other trig functions in general. Well, mostly cosine, but yeah. So we have sine of x, right? But we want sine of 1 over x times x squared. Well, let's look at sine of 1 over x. Is this still true? Can we say that sine of 1 over x is between -1 and 1? Yes, we can, because right? If you look at the graph of sine of 1 over x, well, it also never reaches above 1, also never reaches below -1. And if we plug in large negative values, well, you can see that it probably never ever going to go back up. And if you see over here, it's also probably never going to go back up as well. So the range of sine of 1 over x is also still just 1 to 1, or -1 to 1. And on a side note, sine of basically anything is still also between -1 and 1. Whatever you put in the argument, like sine will always be between -1 and 1. It doesn't matter anything you plug in, as long as there's nothing in the front, this will be true. So so we've got this part covered. How do we get the x squared in? Well, we can just multiply everything by x squared, right? And that should cover that for us. So you get -x squared is less than or equal to x squared. Sine 1 over x is less than or equal to x squared. Note that when you multiply an inequality, by inequality I mean these things, right? The less than or equal to inequality equation, I guess, that what you're multiplying is confirmed to always be positive or negative. And so the reason that's true is because, like, if you multiply All right, so if you multiply an inequality with a negative number, we flip the sign. And if you multiply by a positive number, the sign stays the same. And so the reason why that's an issue is because, like, if you don't know the sign of the number that you're multiplying, we don't know whether or not we should flip these inequalities or not. But in the case of x squared, it's always positive. And you can see that, right? Because if you plug in any negative number, well, you get two negatives, and then double negative is positive. You can also, x squared, right? It never goes below the x-axis, so that's another good reason why we're good in that case. So in this case, we're good to go. We can multiply the whole thing by x squared because we know it's always positive. Cool, and now we have the situation. We have something is less than or equal to the limit. Okay, so now we can just take the limit. Let's apply the limit to everything. Okay, what is the limit as x approaches 0 of negative x squared? Well, if you plug in 0, you get negative 0 squared, which is just 0. This is what we're interested in finding, right? And we don't know its answer yet, and let's do the same thing on this side. Limit is x approaches 0 of x squared. Well, if you plug in 0, you get 0 squared. It's just 0. So our answer, so therefore, by squeeze theorem, this limit is just 0. Yep, and that's 10. Okay, let's move on to number 11. Okay, so find the derivative. Y equals secant 4x plus 3. Probably write in a different color pen. Okay, so y equals secant 4x plus 3. What is this derivative? So I guess we can ask, like, what kind of problem is this? I see a chain rule problem, right? So, right. So now we need to use chain rule, right? So what's the derivative of secant? Derivative of secant is secant tangent, I believe. So secant of 4x plus 3 times tangent of 4x plus 3. Let me just double check that that is true. Secant tangent. Yes. Okay. And then you multiply by the derivative of the inner function, which is just 4. So that's going to be 4 secant 4x plus 3 tangent 4x plus 3. And that's our answer. And then B, we have this thing, right? So y equals 8x squared minus 3x plus 7 to the 5th. So if we take this derivative, it's another chain rule problem, right? I mean, like, you could multiply everything out, but that incredibly tedious. So yeah, it's a chain rule problem. So chain rule, right? What's the other function? It's going to be something to the 5th power, right? So something to the 5th power, that's just 5 times that something to the 4th power, right? And then you just copy what's inside, x squared minus 3x plus 7. and then you multiply by the derivative of the inner function. So it's going to be the 16x minus 3. Yeah, I think that's good enough. Okay, and then y equals root cosecant x. It's another. Yeah. So what's the derivative of y equals cosecant x? Well, y prime is going to be 1 over 2 root cosecant x. Why is that the case? Well, I mean, I just remember that the derivative of x prime, or the root x, is just going to be 1 over 2 root x. Yeah, since root x comes up so often, I just memorized this. Yeah, and then so the derivative of cosecant is going to be negative. Negative. What is the derivative of cosecant? Oh, I would have gotten that one wrong. Okay. Negative cotangent x cosecant x. Yeah. And then just combine everything together. Negative cotangent x cosecant all over 2 root cosecant x. I mean, I guess you could, right? Because this is technically, this is 1/2 power, and this is 1. So this will be negative cotangent x over 2 times root cosecant x. And that's our answer, I think. All right. Yeah, those are all the questions. I'm sorry. Oh my gosh, 2 hours, 30 minutes. I might have gone off topic sometimes, but yeah, hopefully, hopefully this helped. Let me know if you have any questions. Yeah. All right. Thank you.